Dear students, I am giving the 9th video on topology. And initially we start with a definition, that is what the path components. What do you mean by path components? Let X to be a topological space, define an equivalence relation tilde on capital X by X tilde y if and only if the X is a pathwise connected subset capital A of X containing the points X and Y. The equivalence classes of capital X with respect to the equivalence relation tilde are called path components. So X tilde y if and only if the X is a pathwise connected subset capital A of X containing X and Y. That is what the relation. It is an equivalence relation corresponding to this equivalence relation. The equivalence class of X are called path components. Theorem. Each path component of a topological space X to Y is pathwise connected. Let P be a path component of X2. We have to show that P is pathwise connected. Taking 2 points A, B in X in P. Simply A tilde V. That is, there X is a pathwise connected subset capital A of X containing A and B. That is, there is a path joining E and B in capital A. We show that capital A is subset or equal to P. Taking an element X in A, let X in A, so that now small a and X are in capital A. This implies that X is a path in capital A connecting A and small x. Or set X A is a pathwise connected subset of X, or X tilde A. That means X is an element of capital P, or A is subset or equal to P, because already I have taken X in A and that X in P. So A is subset or equal to P. This implies there is a path in P connecting A and B. That means P is pathways connected. Next theorem. Statement. Let collection E alpha to alpha in index set be a collection of pathwise connected subspaces of a topological space X2. Let capital A equal to union of A alpha in index set. If intersection A alpha not equal to phi, then A to alpha is pathways connected. Space A to alpha is pathways connected. Proof. We are taking 2 points AB. Let A be in A. What is A? A is union A alpha. This implies A in A alpha, B in A beta. We can take A in A alpha, B in A beta for some alpha beta in the index set. What is given? Intersection A alpha not equal to phi. So we get A alpha intersection A beta not equal to phi. Take an element there. Choose C in A alpha intersection A beta. That is C in A alpha and C in A beta. Now we get A and C in A alpha, and A alpha is pathways connected. That means there is a path F1 in A alpha from A to C. Similarly, we can prove that there is a path F2 in A beta from C to B. Thus, F1 star F2 is a path in A alpha union A beta from A to B. That is, there is a path in A from A to B. That means A is pathways connected. O A with respect to topology, to A, subspace topology is pathways connected. Next theorem. Each path component of a topological space X2 is a subset of a component of X. Each path component of a topological space X2 is a subset of a component of X. Proof. Let P be a path component of X. We are taking an element small p in P. Hence, P is a pathwise connected subset of X containing this point P. Since every path component is pathways connected. Now P is pathways connected. This implies P is connected. That is, P is a connected subset of X containing this small p. Let C be a component of X2 containing P. That means capital P is subset or equal to C. That means C is maximal and also it is connected. That is Conclusion. One more theorem is important. Next theorem. A topological space X2 is locally pathways connected if and only if each path component of each open set is open. A topological space X2 is locally pathways connected if and only if each path component of each open set is open. Proof. Suppose that X2 is locally pathways connected. Let an open set taking, let U into, and let P be a path component of U. That means P is subset or equal to U. We have to prove that P is open, taking P in P. Since X2 is locally pathways connected at P, and since U is a neighborhood of P, the X is a pathways connected neighborhood V of P, such that P is an element of V subset or equal to U. Earlier definition. Hence, V and P are pathways connected subsets of U, and P is small p is an element of V intersection P. This implies V union P is a pathways connected subset of U. So we must have V subset or equal to capital P. That is, to each point P in P, there is a neighborhood V of P such that P in V subset or equal to P. That shows P is open. On the other hand, or conversely, suppose that each path component of each open set is open. To prove that X2 is locally pathways connected, let P in X and let U be a neighborhood of P. Let P be a path component of U containing this small p. Then by assumption P is open or P is pathways connected implies it is a pathways connected neighborhood of small p, and this small p is an element of capital P which is subset or equal to U. Hence X2 is locally pathways connected at this point P. But P is an arbitrary point. That means X2 is locally pathways connected. Next one is a problem. Show that the continuous image of a pathways connected space is pathways connected. The continuous image of a pathways connected space is pathways connected. So we have to prove. Solution. Let X2 be a pathways connected space and YU be a topological space. We are taking a function f from x to y which is continuous and onto. And what we have to prove? We have to prove that y is pathways connected. Because continuous image is here y. Y is pathways connected. Let A, B and Y 2 points are taking in y. As f is onto, the x is alpha beta in x such that f of alpha equal to A and f of beta equal to B. Now alpha beta in x and x is pathways connected, and there is a path g from I to x such that g of 0 equal to alpha and g of 1 equal to beta. I to x g, I to x g, x to y f, so that I to y, that is f composite g. Consider f composite y, f composite g from I to y which is continuous, and f composite g of 0 equal to f of g0, that is f of alpha is equal to a. F composite g of 1 equal to f of g1, that is f of beta is equal to b. That is f composite g is a path from a to b, or we conclude that y is, capital Y is pathways connected.